components present, which were just bring up that. Yeah. So it had all the three components, which were the convection, that is velocity, or the net convective flow, diffusive flux, diffusion, which is due to axial dispersion, and reaction. All the three components were there. Except that velocity component was very highly simplified. The convection, the velocity convection that is related to velocity, and velocity profile is very simplistic in the sense that it's a plug flow where V is constant. Okay, if it is not a plug flow, okay, and V is not constant, then there will be actually a radial dispersion as well. Okay, if the velocity gradient exists, then there is there's a possibility of having unmixed concentration along the cross section also. Okay, and you may also get actual radial dispersion, but we are ignoring that. Okay, in this current problem. So we started with essentially our main equation was the equation we obtained for the concentration was this one. Okay, so concentration equation was actually this one, and there were the boundary conditions which were given as these. Okay, these two conditions at z equal to 0 and z equal to L, and we can see that z equal to L, it is a Neumann boundary condition, and z equal to 0, it's a mixed boundary condition, which means at z equal to 0 you have both CAZ. The condition is expressed in terms of the unknown and its derivatives. Okay, so this is kind of mixed boundary condition. This is one. Okay, and right. And next, so then what we did was we basically, one of the very standard approaches in modeling engineering problems is to, engineers try to reduce everything in a non-dimensional form. Okay, that is very useful because you are not worried about the units and scales, etc. That will, you talk in terms of non-dimensional quantities. Okay, so here the non-dimensional quantities are defined by scaling them up with respect to respective scales, like scale with respect to C and naught, length is a scale with respect to L, okay, and so on. Okay, and then when you work it out, we are going to get a equation which which appears to be, which is actually a non-dimensional equation and can be written in this form, and then we identified that it's enough to have two combinations of the original constants that we had, that is Vz, L, and D, and K. So there's a two combinations of these two constants, which is enough to represent the actual problem in terms of non-dimensional problem. Okay, we identified these two non-dimensional dimensionless constants, and they have a meaning, physical meaning. Generally, dimensionless constants, or the numbers, dimensionless numbers that we meet in all engineering related non-dimensionalization or non-dimensionalized equations. Okay, those constants usually are related to two competing effects. Okay, so all the numbers that we see, Reynolds number, Peclet number, Proud number, there's so many numbers, Schmidt number, and all these numbers actually reflect, they're kind of they're basically relative weights of competing effects. Okay? What those effects are, that would come out from the expression which is given for those numbers. So here, for example, Peclet number is the relative importance of convective speed to diffusive speed. How fast is the convection? That means how fast things are being transported due to convection versus how fast they are diffusing away. Okay? So these two relative importance of these two competing effects is represented by Peclet number, and similarly there is constant R, which is like field modulus actually, but we will not call it field modulus here. Okay, they are defined with respect to catalyst particles there. Okay, so this is basically reaction and diffusion rates are compared in this. Okay, So these two constants essentially decide the properties of the non-dimensional concentration with length, non-dimensional length or dimensionless length. Okay. All right. Then so now and then we looked at the dimensionless form of the boundary conditions. So the boundary conditions, when written in terms of dimensionless quantities, reads as this condition at z star equal to 0, which corresponds to in terms of dimensional quantity z, it's same as z equal to 0. And when z equal to L, I have z star equal to 1. So I should say z star equal to 1, which will correspond to z equal to L. One gets del CH star or del Z star equal to 0. Okay? So these equations, now everything is expressed in terms of non-dimensional quantity, both the differential equation, okay, differential equation and the boundary conditions. Okay? Everything is expressed in terms of non-dimensional quantity, and then we try to solve CH star with respect to Z star in terms of Z star. Okay. All right. So this is just a representative problem where we are going to apply shooting method. Okay. So what I just discussed is just a model, nothing else. We have not yet talked about the method to solve. Okay. Now let's move on to the shooting method. How do you implement the shooting method? If you recall, shooting method. Okay. So I'll just remind you about the shooting method once again. Okay. So shooting method is okay. So if you recall, you may be given, for example, if you're given instead of z or instead of the value of the variable, you're given the let's say, so the way we had was you had z this independent variable, which I will call it z equal to 0, z equal to 1, okay, and you had let's say you're given a function y. Y is a function of, what we call this x. That's my independent variable x, and y is the dependent variable. Okay. So y values are given to be some value y0, some value y1, yl. Okay. So let's say these are alpha and beta. Okay. So let's see. In my nomenclature, we need to have values alpha and beta. So these are alpha and beta, y values at x equal to 1, y equal to x equal to 0. And then you are specified these boundary conditions, and then you want to solve. So what you do is essentially you start. So what you do here is you have y0 given, okay, and suppose I wanted to treat it as an initial value problem. How would I proceed? In order to proceed from y at y equal to 0, let's say some values alpha is given to me. Okay, this axis is y. And then I want to basically start from here, and at next x I want to find y1, let's say, okay, that at y at delta x value, then 2 delta x, then 3 delta x, and so on. Okay, so at each step I need to know, in addition to y at that step, I also need to know delta y by delta x at that step, so that I can change and then get the change over the next step and add to the previous step, so that I can get the final value. So yn plus 1 will be yn plus del y del x at nth step into delta x, right? So this I can implement. Okay, so at any next step, I can either implement the forward Euler or backward Euler or any other initial value problem solving technique I can apply, and I can get yn plus 1 from y1, okay, can be so I can get y1 plus 1 and y1 if using any method known for IVP. Okay. So, but remember, IVP solves dy over dt equals to f of t comma y, if you recall this. T comma y prime. You can also dy. And you can also have y prime, but let's have this. Now, I also need to know dy by dt at each step. In order to find out, so need dy by dt at each step. Okay. How do I find dy by dt at each step? Now I know y0 from the initial condition, and in order to find y1, I'll need y0 and y prime 0. Okay. What I am given is instead y at L, okay, but I'm not given dy by dx at 0, okay, which I require in order to treat it as an initial value problem. So what we do is instead we assume it's some value. Okay, so y prime 0 is assumed, okay, to have some value, some guess value. Okay, and that with that I solve for y1, okay, and then y prime 0 is known. Let's say y prime 0 we have given some guess value. Now I can solve for y1. If I want to find y2, I need to know y prime 1, right? So I cannot guess at each step, right? The first step is enough, but each step I need to know. I feel like I should have a way to evaluate the y prime 1. So therefore, I need to have an equation for y prime. I need to know how y prime is changing each step. Okay. So to find y prime at 1, I need the wording equation. Like going from y0 to y1, I needed y prime at each step. Similarly, in going from y prime to y prime 0 to y prime 1, I would need y double prime at each step. Okay. So that would be, so I need a governing equation for y prime, or basically how d2y by dx square looks like. Okay. So this is essentially what we are eventually actually what we are actually coming to is a very standard method of decomposing. Basically, now what we are doing is at each step, I'm going to track two variables, y and y prime. Okay. So if I can track y and y prime, I'm done. I can keep on moving. Okay. So from here, I can keep on moving at each step as long as I know how y and y prime look at how y prime can be evaluated at each step. Okay. So if I can find y prime, I can find y. Okay. So therefore I have two equations. So basically this is like decomposing. So decomposing the second order ODE into two first order ODEs. Okay, so we all are familiar with this probably. If you recall, for example, so if you have a, for example, in this case, I have an equation let's say in general I have y double prime equals to some function of y, y prime and x. Okay, this is my equation. That's a second order ODE. Okay, I can change it to first order ODE to first order ODE by defining two variables, y1 prime. Okay, so I'm going well. I'm going to call y prime as y1. Okay, and so I'm going to call y and then y1 double prime. Okay, that is going to be f y y1 dx. Okay, so does that make sense? Right. So I'm going to call a new variable I'm going to use, which is y prime. Okay, that is my now a variable for me. Derivative is a variable for me now. So I'm going to call that y1, and sorry, it should have been prime, not double prime. But y1 prime would be equal to y double prime. And right hand side I write in terms of the variables y and y1. Okay, my variables are now y and y1. Okay. So variables are y and y1. Okay, there are two variables. I can represent it by, let's say, a vector, some vector, call it z. Okay, so so basically this would mean that z prime vector, okay, which is basically z by the x, which is a dependent variable, that is given by a matrix is like so something into, so that would be y1. So let me slide that like this first. This will imply, so I had the equation which looked like z I have identified with y and y prime. Okay, and I know y double prime is some function of x, y, y prime. That's a first order, second order ODE. And then from there I got two equations. One is defining the variable itself, y1 equals to y prime, and y1 prime equals to y1, and y1 prime equals to some function of x, y, and y1. Okay. Okay, so this is all I'm going to do, and then I identify like this. So this can be written as d by dx of column vector formed by y and y1, that is dy by dx, that is y prime, that is equal to this I can write down as y1, and if you look at the first, so dx, so if you look at the first row, dy by dx equal to 0 into y plus 1 into y1. The first row is 0 and 1, and second row is, now second row, this now this thing, as long when only this is linear in y and y1. So now we are going to consider linear in y and y1. Okay, then that is the case we are going to treat. Otherwise I am not able to write this in this matrix form. Remember, matrix represents linear systems. Okay, so as long as we have linear relationship, okay, then I am able to write this as some combination, and there will be some a here, some b here, ay plus by1, something like that. Okay, and should be able to have an equation which can be written in this form. Okay, which is dz by dx is equal to some matrix times z. So we'll look at that. We'll just try to write the current problem in this form. Okay. So this is this first order ODE. Okay. So first order ODE in a vector. First order ODE and I can apply IVP methods to this. You all are familiar with that. Okay, so let's apply the same thing. So now, so what I was telling is, when I start to apply the implicit function. Yeah, right. So yeah, right. So implicit will be, well, it may be implicit, but it has to be linear in any way. And if it's linear, then actually it's explicit. So yeah, so implicit would be actually not there. Yeah, you're right, Amit. So only constraint that I'm imposing is that this will be having some kind of format AY plus BY, something like that. Okay, which we have in our current case. So that's what I'm. Is that all right? Acha. Um, okay. I think you are probably worried about the dependence on X. Um, well, okay. So okay. Let me clarify it here. So I think, okay. So this is one case where linear case will be easily solved, and our current problem actually falls into this category. But if you have non-linear, let's say general speaking, so if f, so now I'm going to Amir's question. He asked, he's worried about x dependence. So let's say if fxy y1, or this equation y double prime is fxy y prime, if it is a general form, maybe having x multiplied with y, etc. So then it is basically, so here I did not specifically consider x dependency. Okay, but now I can actually consider here, if it's in general, I can write down as, I can write this down as dz by dx equals to some function of x and z, right? Because z is nothing but y and y1, y and y prime together, right? So I'm going to write down dz by dx, the combined manner. If it is linear, I can decompose this thing in this particular form, okay, or basically this form. Okay? So f of xz will be having the form of a times a matrix times z if it's linear, if it is having this kind of form, okay, which is a case currently in the current problem. But otherwise also I can write this like this, right? You all, that's fine, and we already know how this is again first order ODE, and we have so remember I had already discussed the relative ease that we get when we have a this kind of form where I can decompose in this a into z form, which is linear in y and y1. Okay, if I have this kind of form, then I can decompose the right hand side, this function in this form, and then it becomes very easy for me to solve. Okay, but even otherwise, if it's not, then the process is a little complicated, but still IVPs can be employed. So for example, if you recall, this one had very specialized and very quicker methods, like for example, this case can be the eigenvalue method can be used for solving this kind of problems, if you recall. But here I'm not able to use eigenvalue eigenvalue procedure, eigenvalue method to solve, right? So here I can use like trapezoidal or Lambda-Katta, etc. Okay? So here I can use trapezoidal, Euler, or Lambda-Katta, etc. Okay? So these can be used for general case. Okay? So the bottom line is, knowing z at x equal to 0, I can proceed and find z equals to z at x, okay, at subsequent points. Okay, can be obtained by employing any of these methods. Okay. And that is basically what is the target. Target is to be able to use these very well developed and accurate methods applicable to this boundary value problem. Okay, so okay, but the problem is that I do not know z equal to x, z at x equal to 0. I only know one component, that is y at x equal to 0, that is alpha, but y prime at x equal to 0 is not given. Okay, what I instead know is y at x equal to L, that is given. I wanted this thing, but this thing is given to me. Okay, so that is the problem. So therefore, since these two components are not known, both of them are not known at x equal to 0, so I do not know z at x equal to 0. Okay, so but what we do is instead we assume some value, and let's say I'm going to call it s. Okay, let's assume some value at x equal to 0. That is initial slope. Okay, once I know that, then I can actually calculate. So then I can use these IVP methods to calculate y at x equal to L. Okay. So using this, I can get some y at x equal to L can be obtained. Okay. Um, let's call that. Uh, let's call that f. Well, give it some name. Let's say h. Okay. Or y equals to L is, let's call that h, which will be a function of s. Is that right? Okay. Okay. So I want I want to choose s suitably, this number suitably, so that h of s matches beta. The last boundary point. So basically, pictorially, we can depict it like you had some initial value given to you, which is alpha. Okay, and you had x this way, and you assume dy by dx to be s initially. Okay, which is like slope, is you assume some slope, and then you know how the slope evolves in this range, which is given by this equation. Okay, you know how the slope evolves, so you know at each step how I can find the slopes. Okay, and also the value, and knowing the slope, I can find the y value itself, and therefore I can actually trace a curve. Okay, I can actually add, so well, it will not be a continuous curve, but discrete points will be obtained at different delta x values. Okay, and then I can reach at the other end when x equal to L. Okay, and here I'm going to get some value which I'm going to call h, and this h will depend on what slope I took initially. Okay. How did I start? So this value dy by dx at x equal to 0, that is I'm going to call s, and h will be a function of s. And ideally, I want hs to have some value which exactly matches with my. So I want to choose my initial slope so that in final value matches with my desired boundary condition, which is beta. Okay. So I want hs to be h of s minus beta to be equal to 0. Okay. So I want h of s minus beta to be equal to this. Let me call this function as g of s. So g of s is basically error that I'm going to, this would be g of s. So error at the boundary with respect to the specified boundary condition, I'm going to call g of s. Okay, and that error I want to basically adjust my s so that that particular g of s is 0. Okay, that's the whole deal. Okay, so basically, so we want ideally g of s to be 0, and that would give the desired s value. And then you have already solved the problem. Okay, because all the intermediate value that you get get by solving IVP using that particular s, which gives you g of s to be 0, is your answer. Okay, that would give desired y of x. Okay. All right. So how do you ensure this? Well, so now here what you do is there's an extension of Newton's method. So you have basically g of s is a function of s. Okay, that is equal to 0. So it's again finding a root of g of s. So I can employ Newton's method, Newton-Raphson, But that's a problem because we do not know analytical form. I do not have an expression for this. I have to compute g of s for every s. Okay, I do not know what is a functional form g of s. No functional form is known. I do not know beforehand that how the error is going to look like for me. Okay, as I choose a given initial condition, I do not know how it's going to look like because that will be a complicated thing. That will depend on what is my step size, what method I choose, etc. Okay, so in its but as it looks, actually, it's a basically root finding problem. Had I known the g of s analytically, then I could have directly applied Newton-Raphson, started with a guessed s initial, and then I could have iterated on s so that until I get g of s to be 0. Okay, so that is what I want to. I do not know. That's one of the uh, obstruction in implementing this method. Well, there's an extension of Newton-Raphson, that's called second method. Okay, for such situations where you need not know the functional form. Okay, and for such cases, there's a second method, which is basically again this is just extension. It's the same thing as Newton-Raphson, except that you do not. Well, it's basically, if you recall, I'm going to write this as delta S equal to minus g of xj divided by d of xj minus d of xj minus 1 into xj minus xj minus 1. So it's the same thing. If you recall Newton-Raphson, if you knew the function, what was delta S given by? So x, if you recall, I'll just write this as xj plus 1 equals to xj minus fxj divided by f prime fj, right? What we are doing here is nothing but approximating this quantity. Since I do not know the functional form, so I cannot evaluate f prime. So instead I will compute f prime by doing this operation, which is I'll compute f at xj plus xj minus f of xj minus 1, and then I'll divide it by xj minus xj minus 1. So that we can over to xj minus xj minus 1. Okay, these individual values I can calculate. Okay, and then plug in these numbers, and I will get equation that looks like this. This is essentially the same thing here. Okay, so if I do not know how to calculate, if you do not have the functional form available for a function which has to be set, for which you have to find a root, is the case over here. So in that case, I can apply slightly modified Newton-Raphson method called second method, and this is the scheme for that. Okay, it's essentially the same thing, except that what you do is you start for any step, you know the initial slope. Okay, and you knew the previous slope. Okay, I mean, you knew the error with the current slope, you knew the error with the previous slope. Just do this operation. That you are done. Okay, so you know how to modify my s at each step. Okay, now there's one issue that you have to be careful is that so for example, let's say I knew say s and j here is so there are basically two things. We will go back. Okay, so here what I'm going to do is first I'm going to take, let's say j equal to 0 would correspond to my first complete pass from here to here. That will be j equal to 0. Remember, j equal to 0 is not this point. J equal to 0 would be one complete IVP. Each j will correspond to one complete IVP solve, one complete march from left to right. That will be one j. Okay, so j equal to 0 will be the first march from left end to right end. Okay, one boundary to the other boundary. That is what you have to be. Don't confuse here. So I'll just write it down. Each j implies one complete march. Okay, from left boundary to the right boundary. Okay. All right. So with chosen Sj, okay, 0 would be the first one. I found some G for that particular Sj. Okay, that would be this error. Okay, and so I know G0. So let's say I guessed as S0. Okay, so I guessed S at 0. K is equal to 0, or let's call this 1. Okay, that's confusing in MATLAB. Does not take first in the element index to be 0. So let's say J equal to 1. That's the first guess. Okay, and then from there I calculate G of S1. Okay. Now, is that enough for me to give me G at S2, or do I still know how I'm going to update S1 now? My first slope was S1, and do I still, by doing this calculation, actually it's not still sufficient for me, this information is not sufficient for me to be able to update S value. Initial slope that I'm guessing, we cannot still update. Even though I know GS1, I do not know delta S until I know 2 GS's value, which are 2 consecutive iterations. Okay. So what I can do is, so I have to actually do 2 guesses. So here I have to make 2 guesses. Make second guess. Okay. Second guess would be, let's say, S2, and then from that you get an error at the other boundary, which I'm going to call S2. Okay. So now I have 1 and 2 given. Okay. So therefore I can calculate GS2 delta, that will be delta Sj. So I can calculate G delta S2. Okay. So now I have right hand side J equal to 2. I can take J equal to 2. So GS2 is known, GS1 is known. Okay. S2 and S1 are known. So right hand side is known. I know delta S2. So from here I can actually calculate delta S2 now. Okay. So that's to remember here. I have to make 2 guesses. Not one guess is not enough. Okay. In order to be able to implement this formula, okay, I have to have 2 initial guesses. So using those 2 initial guesses, then we are all set. And then so delta S2 is known. Update S2. S3 will become S2 plus delta S2. Okay. And with this new S3, we again take a march from left end to right end. You keep on. So essentially, what you're doing here is you are basically testing your initial slope, okay, according to the error that you're getting at the other end. Okay, and there's a rule for adjusting that slope, which is given by this formula. Okay, the rule that governs how you adjust your initial slope is given by this particular formula. Okay, so that is the whole picture of applying this this method, right? Any question on that? Simpler way. Tell me, Rohit, what do you mean by a bit simpler way, meaning what? I mean, is this all appearing, sounding too difficult? Rohit, just let me talk to you then. Just a minute. Okay, is this appearing complex for you? Well, so okay, well, okay, so partly it's my fault. Probably I'm making it. I sound complex. Let me go back then. Let me go back and ask you which step do you find? Do you first of all do you understand the idea, the basic idea behind this implementing the shooting method? Rohit, am I audible to you?
Yes, sir. Yes, sir. Next page, sir. Next page ऊपर है, sir.
Next page के
ये सर, ये जो मिडिल में लाइन खींची है ना सर, इसके नीचे का कुछ क्लियर नहीं है सर मेरे को तो.
अच्छा, तो यहाँ से हाँ. So ये मैं बोल रहा था कि see what I was saying is कि Okay. So, well, if you write this equation here, so if I have an equation, remember second order equation, I had, I don't recall, let me go back, how I had defined that. I guess I had defined generally plus 2x y prime plus 3x y something like that. I think I had started with this form. Second order linear. So this is the kind of equation I have. Now I can write this as y double prime is equal to this is only still not a linear. Okay. So I can write down hx minus ux y prime minus ux plus 1. Okay. So here, well, you can, this is linear equation, right? So you can write this. So suppose I have this kind of form. Right? Please stop me if you are not able to follow anything, but right then and there itself. Okay? So remember, this is a linear second order ODE I'm looking at. And this I can write down. Suppose I define a quantity y prime as a new variable, okay, and call it y1, and then y1 prime, which is y double prime, is given by h of x minus ux into y prime, which is y1 itself, minus v of x y. Okay. So if I take this and let me write it over here. So I have y prime, okay, and y1 prime. So that would be written as some constant into I plus some constant into y1. Okay. And here that would be a1 b1, then a2 y plus b2 y1. Okay. All right, this is all right. Where now a1 is 0. If you look at this expression, I have nothing multiplied with y. Okay, so v is 1. Okay, so v will be 1. Okay. And similarly, a2 here, and actually there will be additional h of x. So I'm going to ignore, let's say h of x is 0. Otherwise, you'll have a constant term here. So there will be a constant term h of x. But let's assume that h of x is 0 now. Okay. So with that, that will not make a big difference actually. So let's assume that h of x is 0. Okay. So in that case, I will have u of x y1 minus v of x y. So that will fit into over here. U of x in v of x will be a2 and u of x will be v2. Okay. So then I can write this as y and y1 entire primed equals to some matrix A, okay, which will be having the form which looks like form that looks like 0, 1, and minus v of x minus u of x y y1. ठीक है, it is all right. Yes or no?
Yes, sir.
Yeah. Okay. So now I have this form. This, so we are assuming, of course, this will be 0 for now. Remember. Otherwise, there will be a constant added to it. Don't worry, because that will be independent of your y or y1. So there will be a constant added. That won't make a big difference. So this is the equation. So this form I'm able to write because why am I able to write this? Because I have initial equation, differential equations linear in y and y prime. Okay. However, there are other complicated cases where I'm not able to write this one. Suppose I have product appearing, so I have an equation that may look like Probably all are familiar with what is a non-linear differential equation. Okay, so 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 in case of a non-linear second order ODE, okay, I am unable to write the differential equation in the following form, which is y double prime plus u of x y prime plus u of x y equal to h of x. This you cannot write, okay? Because you will have terms like y into y prime, or suppose I have an equation that looks like y double prime equal to y prime. Okay? That's a very simple second order non-linear differential equation. I cannot write it in this form. Okay? That's not possible. So what I said is there are two levels of there. Basically, I've just divided the problems into two classes. One is simple one, which are linear, but at the same time you can have non-linear kind of problems which you cannot write in this form. Okay, so even those can be treated. Okay, that's all I'm saying. Linear ones are special in the sense that there are very simple and quicker methods devised to find out if you have basically, if you can write this d by dx, it's a y and y1 equals to some matrix y and y1. Okay, I have some ABCD or something like that. Okay, now I have a very smart methods known for me. This is the reason we are treating this separately is that there are some specialized methods which can be utilized for solving linear problems. Okay, but that does not mean that we cannot solve nonlinear ones. Okay, so that's the reason I just distinguished these two different cases, right? So other cases when I cannot write in this form. So how do we write this then? There's a simple, there's a way we assume that equation to have this particular form. Okay, so this may be a nonlinear function. Whatever we apply for nonlinear function can equally well be applied for linear case. That's fine, but we cannot go reverse. We cannot apply these specialized method for linear ones to nonlinear ones. Okay, so that is why I am taking this case separately. Does that make sense, Rohit? Rohit, does that make sense?
Yes, sir. Yes, sir.
Okay.
I'm following.
Thank you. All right, okay. So let's move on. Okay. All right. Amit has a question. Let me see. Until, yeah, of course. Well, yeah, of course, zero. Well, you never get ideally zero, so you have to define a tolerance limit. And when you get g of s is zero, or you are not improving much, means delta s tends to become have a value zero. Okay, then you stop. In either of the case, these two conditions may coincide, which may happen which would happen when g of s is actually a root, but it may so happen if your method that you're using to solve your IVP is not good enough. Okay, that means the method that you're using to solve from in going from left end to right end, if that you're not using good method, then it may so happen that you may keep on getting delta s 0, but gs may not be 0. Ideally, you want gs to be 0. Okay. You also want to stop in such cases. You cannot let your code run for eternity, right? Suppose delta s is approaching 0, but g of s is not approaching 0. Okay. Then you know that there's a problem in my IVP solver, okay, or something is wrong in my code. So you want to stop then and then recheck. So you want to stop not only because you have found an answer, you also want to stop because you are unable to find an answer. Okay? So therefore you have to have both the conditions in your code. That means either this is 0 or g of s is 0, or within the tolerance limit, whatever tolerance you decide should be less than that tolerance limit, 1 10 to minus 6, 10 to minus 12, whatever you decide. Okay, so that Okay, just a second. Well, I should not. There is a the question is the possibility to obtain multiple roots for S. Well, you're not getting roots for S. Yeah, G of roots of GS. It should not. Should not. Uh, well, since we do not know the mathematical form of G of S, I cannot comment. Okay, but all I know is that what if you get G of S to 0, okay, then you should be happy enough to find even one root which is real value, real root for if you find some S which gives you your boundary condition satisfied, the differential equation in between satisfied, then why do you worry whether you have another root or not? You have found an answer. Actually, you are basically suggesting the you are basically trying to find an answer of uniqueness of your answer solution. There is a very important issue in mathematics about uniqueness and uniqueness of a solution. Uh, so, well, we'll assume we are not going to go into those mathematical issues. If I have found a solution, we'll assume that is the solution. Okay, there's always a unique solution there, and we'll assume that there are multiple. There may be multiple solutions, but I think in mathematics they spend in pure mathematics they spend quite a lot of discussion on proving the uniqueness of a differential equation based on its specified boundary conditions, etc. Okay, we'll assume that if I have found one solution at least, then that is the solution we want it, okay, and we'll be happy with that. Okay, so yes, there is in general I cannot rule out non-uniqueness, okay, but we'll be happy with our solution. Okay, as an engineer, I'm not going to worry about whether there are multiple routes. All I know is that my system should be happy, and as long as boundary conditions are satisfied and the differential equation is obeyed in in my concerned range of x, I'm happy. Okay? That's all we want to ensure. And as long as I have a case that ensures these conditions, we are done. All right. So I hope that satisfies your question. But that's a very important question actually. Okay. So now let's move on. Let's go back to our problem of axial dispersion one. So I'm just going to try to look at some of the important issues. So this is what I just described is most generally applicable. Okay. Now we are going to apply this whole idea to our back to problem of EFR with axial function. Okay. And we had these equations that read as after non-dimensionalizing, we check the notes. Going back to it, I'm just copying it down from my notes. Okay, and if I define a quantity, a vector quantity y, which is essentially C star x, okay, which are the value of the derivatives, that would imply I can write this as y by z star equals to a vector a matrix into y, where a will have a form that would look like 0, 1, r, and 4. Okay. So that is what it essentially boils down to. Okay. And that would fall again to this is basically a linear problem. Okay, you look at the differential equation that we obtained, it was a linear differential equation. Okay, that's why we are actually we have a simpler problem to solve, not a nonlinear problem. Okay. Okay, so having said this, all I need to know is now how to solve this. But besides that, I need to have the boundary conditions in place, right? So what are the boundary conditions? Conditions. This is a differential equation. Boundary conditions read as CA star at CA star minus 1 by factorial number del CA star by del Z star equal to 1 at Z star equal to 0 and del CA star by del Z star equal to 0 at Z star equal to 1. These, so this is a set of differential equation, and these are the boundary conditions. Together, I have entire problem specified. Okay, and this I am able to write no matrix form. Okay, for the purpose of implementing numerical computing. Okay, okay. So now, having developed a model, now you want to solve it. Now, how do we solve it? So now, as this problem is little complicated in the sense that I do not have the boundary condition specified in a very simple manner, because at one end, okay, z star equal to 1, that is at the right boundary, I have the derivative equal to 0. The condition is expressed in terms of derivative. The left boundary, I have the condition expressed in terms of both value and the derivative, so mixed boundary condition, right? So, how do you do this? How do you proceed this about this? So there. First, I'll just outline one method, and I want you to do actually this exercise, and this will be due next week. Okay, next Monday, I want you all to submit your MATLAB codes. So this is important because this will actually, if you do this exercise, you will know how to integrate all that you've learned so far, which is Newton-Raphson technique, IVP, initial value problem solving, and the shooting method. All the three will be combined. Okay, so everything that you learned so far, quite a bit of it will be actually able to use in a single problem. Okay, so I want you to solve this. Okay, so method would, so there will be one way. So one of the ways I can use is using shooting method. Okay, so let me write down my boundary conditions once again over here. If star at U star minus 1 by the number U star by the star equal to 1 at Z star equal to 0. Okay, it's 2 more minutes and I'll be done. Let's U star by the Z star equal to 0 at Z star equal to 1. Okay, these are my boundary conditions. Okay, so what you do here is, first method you have, what I want now is you can assume del CS star by del Z star to have some value. Let's call that S. Okay, at Z equal to 0, because that is not given to me. Okay, I have del CS star by del Z star specified at the other end, or the left end. Okay, so if I want to start from left end, then I will assume this. Okay, and then compute CA. At the same time, I have not CA star 0 is also not known. I need both CA star and del CA del Z star at left end in order to implement my IVP, okay, methods, right? So now CA star can be actually obtained from this boundary condition, the first one. Okay, so compute CA star using first boundary condition. Okay, which is this one. Let's call this number 1. Okay. So having done this, then compute C star at Z star, okay, using first order initial value problem solver. Okay, and then you update your S based on second rule that I gave you. Okay, because CA star at Z star, okay, try to match, then try to match the boundary condition number 2, second boundary condition, okay, which is this one. Okay, so you can basically define G of S, that is error, would be you want this quantity to be 0. So basically del C by del Z, del C star by del Z star at Z equal to 1, Z star equal to 1, that would be your G of S. Okay, that I can evaluate by solving this, and then if you know G of S, I know how to calculate. Then you can calculate G of S0 and G of S1 and G of S2. I have to take two guesses about this quantity, the left edge slope. I'll take initial two guesses, and then I'm all set to calculate G of S3 and so on. Okay, G of S4 can be obtained, etc. And then eventually you keep on iterating until you get a desired tolerance limit reached, and that is done. Okay, so that is your one method. I want you to implement this, and well, try this, and I'll talk about the other method with slight modification of this. Okay, the next class you can implement that. Okay, so any question on this? So that will be your homework. Uh, so take, for example, some realistic values of those. Well, actually, you can start with some Peclet number and some R value, okay, and find out by implementing this shooting method how CA star changes with Z star for a given set of Peclet number, and then you can play around with Peclet number and R to see how things change, okay, and what are the difficulties you might face. You have to let me know, okay. So please do that. So homework, solve this, okay. Using, so use any of your favorite initial value problem solving method, right? It can be trapezoidal or radial or K4, etc. I would recommend using Ranjan fourth order, because accuracy is important here, but it's up to you. Okay. Well, actually, by now you should have been able to implement. You know how to implement different techniques, and you can check which one is good, which one fails, etc. So you have to do a little bit of analysis. You have to do a little bit of playing around with these different techniques. Okay, using any IoT solver. Okay, using the table number. And, okay, so any questions? I expect this by next Tuesday or coming Tuesday. Okay. All right. So that's it. That would be 29 pages. All right. So please do that, and we'll meet in the next class. All right. From the class for that.